All right, this lesson is about light, which is more appropriately called electromagnetic radiation. That's what this word says, big long word, electromagnetic radiation. And so that's kind of the first thing we need to talk about is that when we use the word light, typically we are always referring to this stuff that we can see, the things that are coming off of your computer screen right now. We say that is light. Well, actually, as you've realized with many things in this class, light means more than that. So we're going to talk about exactly what light is, which might not have been a question you asked yourself, but you'll find today, I hope, that it's more complicated than you thought. All right, so light is, first of all, a wave, and it's a transverse wave. We've been talking about energy that travels in the form of a wave. We've talked about waves. We've talked about sound. Now we're talking about light. Light is energy that travels in the form of a wave. It's radiant energy, right? So just like the battle ropes is a wave, light is also a transverse wave. And, I don't want to explain the complications of these diagrams. We don't have to worry about that. All I'm putting this here for is to let you know that light is indeed a wave, and it's a transverse wave. It's not a compression wave like sound is. Light is actually the only wave that can travel through empty space. And so it's important that we know that there are two distinctions, two categories of waves. One is transverse and the other is compression. But now we have two other categories, one of which we've talked about already. Mechanical waves, remember, that was like sound. Mechanical waves require a medium to move through. Light does not require a medium. It can travel through empty space. And the reason light can travel through empty space is because of, as this diagram shows here, because of the fact that it can actually propagate itself. A mechanical wave uses molecules and particles to propagate itself, but light doesn't do that. So it doesn't need molecules to propagate itself. It can move through a medium. It can go through air or water or glass. But if it does that, it slows down because it doesn't use those molecules to move. It's just that the molecules get in the way. Similar to you wading through water. You can walk through air much easier than water because you don't use the water or the air to move yourself. You are self-propagating. And so since you're self-propagating, when you're in water, the water molecules simply get in the way, which means you can't move as fast through the water. And light is the same way. Light is fastest through empty space, through a vacuum, where there is nothing. And light is the only thing that can travel through a vacuum. The last thing you need to know about light is it is crazy fast. It's the fastest thing that we know of in the universe. 3 times 10 to the 8th meters per second, or 300 million meters per second. And that speed is the first thing we need to talk about here. You don't have a way to understand just how fast light is. So let's start here. 300 million meters per second. So up until this point, you may have thought that when you turn on a light bulb, everything just instantly gets lighter, right? You see the light in the room just instantly. As soon as you turn the light on, the whole thing gets bright. And it makes us think that it is literally instantaneous. It makes us think that this light reaches our eyes literally instantaneously, lighting up the room around us instantaneously, but that's not actually the way it is. And if we could slow this down, it actually does take some time for the light to reach the room around you and for the light to reach your eyes. Now, it's really, really fast because, again, the speed of light is 300 million meters per second. But it does take a little bit of time to get there, and this is a exaggerated, slowed down animation of that fact. All right? So light does have a speed. It's not instantaneous. It doesn't reach us instantaneously. It takes a little bit of time to go from one place to another. And that speed is really fast, right? So let's talk about that speed. The speed of light is the reason why in a previous lesson I talked about thunder. The fact that when you see the lightning, it happens almost instantaneously. But the thunder that you hear happens way later, right? So you see the lightning first, almost instantaneously, and then you hear the thunder later. And the reason is because sound is way slower than light. Light travels over 882,000 times faster than sound. It's an insane comparison. Light is ridiculously fast. All right, so at the speed of light, let me give you a few things you can do. Hopefully this will help you understand how fast light is. So at the speed of light, it's 671 million miles per hour, just to put it in context of our units. But you probably still don't have a great idea about how fast that is either. So let's take it down to seconds. It's 186,000 miles per second. But that doesn't really do a lot for us either. So let me tell you what you can do if you're moving at the speed of light. If you're moving at the speed of light, you can go around the circumference of the Earth in 1 second. 7 times. Now think about that. 300 million meters per second. You can go 7 times around the Earth at its circumference in 1 second. Guys, that's crazy fast. So now we're kind of starting to get a little bit more of an idea about how fast light is. What's really interesting is that when we move out, when we zoom out on kind of a planetary scale, the speed of light starts to make things have a really interesting effect. All right, so over here on the left we have our sun. It's the nearest thing to us that produces light. Our sun happens to be approximately 93 million miles away from us. And again, light from the sun does not reach us instantaneously. At that distance, for light, once it leaves the sun, it turns out it takes about 8 minutes for light from the sun to reach us here on Earth. So that means if the sun blew up, we would have no idea until 8 minutes from now. There's no information. There is nothing that travels faster than the speed of light. There's absolutely no way to know what is actually happening. This is kind of interesting. There's no way to know what is actually happening right now, this second, on the sun. The only thing that we see on the sun is the way the sun looked 8 minutes ago, because it takes 8 minutes for that light to reach us. All right, so let's zoom out a little bit more. Instead of the sun, let's move outside of our solar system. When we get outside of our solar system, we can't measure distances in meters and miles and kilometers anymore. They just won't work. It's similar to measuring the distance of a race in centimeters. It's just not going to happen. And so what we're going to do is measure distances in light years. Many people think a light year is a unit of time, but it's actually not. It's a unit of distance. A light year is the distance that light travels in 1 year. Now I want you to think about that. Remember the speed of light, 7 times around the circumference of the Earth in 1 second. At that speed, imagine doing that speed day in and day night, 24/7, 365, for 1 year. And in that amount of time, moving at the speed of light, it turns out you would cover a distance of about 5.88 trillion miles. So 5.88 trillion miles is a light year. It is 1 light year. And so we're going to use light years as the distance measurement, as the meter stick for outer space. So let's move out from our planet and let's look at our closest star. The closest star to us, other than our sun, is called Alpha Centauri. Alpha Centauri happens to be about 4.4 light years away from us. If you want that distance in miles, you'll have to take 4.4 and multiply it by 5.88 trillion miles. So 4.4 light years away. Are you ready for the mind blow? That means that when light left this star 4 years ago in December 2015, tonight when you go out to look at it, it will just now be reaching Earth. It has been traveling at a speed of 300 million meters per second, day in, day out, for 4 years. And just tonight, we'll be able to finally make it to Earth, to reach your eyes so that you can observe it. But that's the closest star to Earth. 4.4 light years away. Let's zoom out a little bit more. Here's something that might look familiar to you. This is a constellation in the northern sky typically, and it's called the Big Dipper. We typically call this the Big Dipper. There's one star in the Big Dipper that we're going to pick out, and it's called Merak, is the name of this star. Merak, as you might be figuring out by now, is a pretty long way away. Alpha Centauri was 4.4 years away. Merak is 80 light years away. That means tonight when you go out and look at this constellation and you see that star, you are actually looking at light that left the star 80 years ago in the year 1940. Guys, that's before World War II. So when Adolf Hitler was doing all of his stuff, when all of that was going on before, the Third Reich, before World War II actually started, before the Holocaust, or during the Holocaust actually, before liberation, light left this star, and just tonight, those photons are going to get here to Earth to reach your eyes. Just a few more. I want to look at this one. Here's another familiar constellation, probably the most famous one. This one's called Orion. Orion is in the southern sky in the wintertime. And he's an archer, right? Here's his bow. But I want to focus on the right shoulder of Orion. It's a star called Betelgeuse or Betelgeuse, however you want to say that. Betelgeuse, as you might be figuring out right now, is very far away, much farther than the previous star. Betelgeuse is 643 light years away. So that means light left this star to get here tonight 643 years ago. Y'all, that was the year 1377. I don't even know what was going on in 1377. But that was a long time ago. And just now tonight, the light's going to reach your eyes so that you can see it. So that means you may have even known recently astronomers have been noticing that Betelgeuse has been changing shape, and there's been a lot of speculation on whether or not Betelgeuse is going to blow up. But guys, if it happened, we wouldn't know it until 643 years from now. We're looking at Betelgeuse the way it looked 643 years ago. You're looking at Merak the way it looked 80 years ago. You're looking at Alpha Centauri the way it looked 4 years ago. So that means it's impossible to look into our night sky and see things the way they look right now in this moment. Because even though the speed of light is very, very fast, the universe is so big that the speed of light is actually pretty pokey in terms of our universe. Here's some other things you might have heard about before in our universe. The star Sirius is 8.6 light years away. Vega is 25 light years away from us. The star Arcturus is a really big one, 36.7 light years away. Pleiades, this is actually the Pleiades that you see behind this. It's an open star cluster, 444 light years away. Antares, 619.7. The Horsehead Nebula, a beautiful nebula. You might have seen pictures of this. 1,500 light years away. To see this nebula tonight, you go out and look at it, and light left the stars and the things in this 1,500 years ago. The Milky Way galaxy, our galaxy that we live in, is 1,000 light years from side to side. If you were traveling at the speed of light, it would take you, not 1,000, 100,000. It would take you 100,000 years to get from one side to the other. And this is just our galaxy. Guys, there are 100 billion galaxies in the universe, many of which are very, very far away. And one of the farthest away that we've ever observed is called the Sombrero Galaxy. You can see it looks like this, kind of like a sombrero. Guys, it's 29.3 million light years away. When we see it, we're looking at the way it looked 29.3 million years ago.